Have you ever been caught in a sudden torrential downpour and wondered where all that water actually came from? It feels like the sky just opened up and dropped an entire lake in an instant. It turns out that most of that heavy summer rain doesn't start as liquid at all. Miles above your head, almost all severe rainstorms begin as jagged, frozen ice crystals. When those high-altitude ice storms melt and dump their water over a city, streets can turn into rivers in minutes. Rescue crews often have to navigate waist-deep water just to reach people stranded in their cars. The challenge is timing. To know exactly when and where a flash flood will hit, we have to understand exactly what those tiny ice particles are doing way up in the freezing atmosphere. Keeping communities safe from these floods depends on understanding the specific physical laws that govern how water behaves when it gets extremely cold. For decades, experts followed a strict set of rules. They believed ice crystals only multiplied in a very narrow, slightly freezing window, specifically between -3 and -8 degrees Celsius. But to see what actually happens inside a storm, researchers began scanning the atmosphere with advanced orbital sensors, looking deep into the heart of the clouds from space. Their instruments detected sprawling swarms of ice crystals in the highest, coldest reaches of the cloud, areas where the textbook said ice should be sparse. The data showed ice multiplying rapidly at a freezing -27 degrees Celsius. That is nearly 20 degrees colder than the zone where scientists thought this was even possible. Finding ice expanding at -27 degrees meant there was a missing piece in our understanding of the atmosphere. Some unknown physical process was creating all this extra ice. What they discovered is a physical chain reaction. In the scientific community, this is called secondary ice production. Think of it like a popcorn machine, where one event triggers a non-stop burst of new activity. It starts with droplets that are still liquid despite being way below freezing, similar to how a bottle of soda stays liquid until you bump it. When these droplets finally start to freeze, they form a hard, icy shell around a liquid core. As the water inside that shell continues to chill, it expands. This creates crushing outward pressure against the rigid, frozen casing. Eventually, the shell gives way. The droplet violently shatters, shooting dozens of microscopic ice splinters in every direction. These new splinters fly through the cloud and strike other liquid droplets, causing them to instantly freeze and shatter in turn. As this diagram shows, one particle becomes dozens, which become hundreds, spreading like a falling row of dominoes. Because this growth is exponential, it only takes minutes for a small cloud patch to fill with billions of ice crystals. This microscopic shattering is the engine that drives a storm. It's the process that turns a normal cloud into a factory for intense precipitation. To track these engines, meteorologists use sophisticated digital simulations. These work like a video game physics engine, where computers calculate how millions of virtual water particles interact to predict the weather. There are two main ways to run these digital models. The first is called the bulk method. You can see the bulk logic on the left. It groups all the ice particles into broad, simplified categories like snow or cloud ice. By simplifying the shapes, the computer can run the simulation very quickly, though it loses a lot of detail. The alternative is a much more detailed tool known as the bin model. In the bin approach, the computer precisely sorts particles into dozens of individual compartments based on their exact size. It gives a much more accurate picture of the cloud, but it requires vast amounts of computing power to process. But here is the problem. It doesn't matter if a meteorologist uses the fast model or the detailed one. If the computer isn't programmed with the rules for how ice shatters, the forecast will be wrong. Because this discovery is so new, our older computer models didn't know that ice could explode and multiply at -27 degrees. Now, researchers are actively rewriting the code. They are updating the math in our simulations to include these new rules for how ice shatters and multiplies in extreme cold. This update allows our virtual models to finally match the real world. By accounting for the way ice behaves at the microscopic level, we can better predict when a colossal storm system is about to develop. Understanding how water behaves in the freezing upper atmosphere is the key to mastering our climate predictions. The more we learn about these tiny crystals, the better we can protect the people living beneath them.